a high Reynolds number drag question. So, and it's a high Reynolds drag number question at terminal speed. So at terminal speed, I know the drag. Oh, you can't see. That's a good point. Okay, all right. So drag, the magnitude of the drag equals the magnitude of the weight. So in this case, 1/2 CD rho A VT squared. So I put the T because it is the terminal speed equals mg. So I'm trying to solve for A. So the A is equal to 2 mg divided by CD rho VT squared. So if you want, I'm not sure if you that's the process you followed. If you want to take a second, you could go ahead and calculate that. Top line, so 8 grams, so 8 by 10 to the minus 3 kilograms. Make sure you can make that conversion. Times 2 times 9.8. I think that should, the numerator should give you something like 0.157. And that must be in newtons. It's kilograms times meters per second. I'll maybe just leave out the units, it's get complicated. And this stuff down here in the bottom, 0.5 times 1.2, and then square the speed, the 5.8. And that should give you around 20.2. So the area works out to be pretty small, because a meter squared is very large, 7 meters squared. So a meter squared, again, is a huge area, so a leaf is, small leaves are only a tiny fraction of a square meter. Questions so far? Yep.
So the terminal speed, that isn't actually using the calculation. That's just saying that is the terminal speed, but the weight and the drag are going to be equal regardless of what the terminal speed is.
So the question is about, I think, regarding terminal speed, the terminal speed is only the speed of the leaf when it is when the drag equals the weight.
Right.
So that speed only refers to when it's the drag equals the weight. There's no net force on the leaf.
Right, and that force, that's not being used in the calculation.
It is in the fact that so in this equal sign, so in order to equate these two, I have to know the drag equals the weight. So it's a circular leaf. The area, it's basically the surface area that matters. It's also the same for a sphere, that you need to know. So in a sense, it's not always the surface area. So it's usually the cross sectional. It's the cross sectional area that matters. I'm recording this. Let me just check. Yep. So since it's just a leaf, it only the cross sectional area is just the area of the leaf itself, but if it's a sphere, it's also the cross-section area, is also a circle. So the area is equal to pi r squared. It's also equal to pi over 4d squared, but most of you I think are more familiar with this phrasing. So you could also do pi over 4d squared and set that equal to 0.077. So if I wanted to find, you can find r, you can multiply by 2, you find d, and maybe since we're finding d, I would then get square root of 4 times that area divided by pi, and you should end up with 0.1, I'm guessing. Yep, you have to end up by 0.1 meters, which is 10 centimeters. Question?
So when you're kind of making that assumption that you're just equating the leaf to like a circle, how would should we always just assume, like when if you give us another object?
I had to tell you the leaf is circular.
It has to be a circle.
Well, I state that it is in the question. So I have to give you the shape in order for. So if I said it, I might say a square, a square leaf that has a length L, or like so. Then I went down here and asked you, what is the side of the square leaf? What is the length of the side of the square leaf? Or if it was a sphere, it's the same thing as elastic, but a spherical leaf doesn't make any sense. So I would have to pick a two-dimensional surface, but if it was another object like a ball or cube falling, remember that it's only the cross-sectional area that matters. But yeah, I had to give you an object that you know. That I guess I want you to know, expect you to know the area of a circle, so you could solve the problem.
Give us a three-dimensional object.
Yeah, I could.
And we'd still just take the area.
You'd still take the cross-sectional area, yes.